Hey chemistry students, Mr. Ferguson here. We're going to do lesson 10.6, where we're going to put things all together, stoichiometry and the ideal gas law. So what we're going to ask you to do is to solve stoichiometry problems that involve conversion of gas volumes at both standard temperature and pressure conditions and at non-standard conditions. I'm going to give you the good news right now. There is no post-video question at the end of this. But we are going to go through and work out several problems of this type, and we'd like you to follow along and put that in your notes, and then we can pick up here in class the next time. So let's get started.
So for these problems, we're going to require the use of the gas laws as well as the reaction stoichiometry. And the key gas law that we talked about last lesson was the PV equals nRT. This gas law can be used to derive any other gas law, and if you don't remember the other gas laws, you can use the ideal gas law to pretty much figure out any problem as long as you're willing to do some extra math. And if you forget, the molar gas volume at STP is 22.4 liters. If you forget what STP is, that's 1 atmosphere and 273 Kelvin.
And we actually will need to remember those two facts because we end up substituting those into the conditions like in the combined gas law or something in some of these problems. So just to also review, we've got the other gas laws. You should, that Boyle's law is P1 V1 equals P2 V2. So we paused the video and just wrote out all of them. These are all the gas laws, which again, you should know them already. Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's, and the combined gas law, and like we said, the ideal gas law. So you've got all those kind of in your toolkit now, and you can pick the one that you need to get you to the answer.
Let's just try a practice problem with this.
So what we have here is a screen capture of one of the problems in your packet. This is problem 2. It's at the top of page 44. And you're going to be assigned to do a number of problems like this, so we thought we'd choose one and kind of show you how to approach it and work it out. So this is a type of reaction stoichiometry / gas law problem. So let's work out each of the 3 parts of the problem, and we'll talk you through it. Okay, Mr. Hunter, let's get started.
So it says propane burns according to the following equation. It's propane plus 5 oxygen yields 3 CO2s and 4 waters. So they first want to know what volume of water vapor measured at 250 degrees Celsius and 1 atmosphere is produced when 3 liters of propane at STP is burned. So the first thing we need to do is stoichiometry in this case, because we know we have 3 liters of propane. So our start point is 3 liters
of propane. That would be
C3H8. And we're going to convert that to liters of water.
Okay, so we want to see how many liters of water we're going to get as a product from the combustion of that. And since it's at STP, like you said, we're just going to straight up do it as a stoichiometry problem.
At first.
Okay, so we know that, 22.4 liters of any gas, so propane is a gas, C3H8, is 1 mole of that gas.
And you got to use your mole ratio, of course, going through that mole island. So it's a 3 to 1.
For every 1 liter of that.
Oh, 4. Sorry, 4 to 1.
4 liters of water, 4 moles for every 1 mole. For 1 mole C3H8, 3 moles H2O.
And then finally, of course...
So that's 4 moles, isn't it? Sorry.
Yeah, it is 4.
4 moles.
So then finally, for every 1 mole of H2O, there are 22.4 liters. So this is going to equal out to 12 liters of water using proper sig figs.
12, no decimal.
No decimal.
No
zero. H2O.
12 liters H2O. And that, we need to note, is at STP conditions. However, go ahead, Mr. Hunter. What's the however?
However, since we know that this is at STP and they tell us that this ends at 250 degrees Celsius and 1 atmosphere, this tells us now we're going to have to convert our volume at the end. The good news is it's at 1 atmosphere at the end, and we know that at STP conditions the pressure is 1 atmosphere. So we have to decide which gas law we want to use, and in this case you can wind up using volume divided by temperature equals...
Because those are the only two things that are changing.
So this would be your Charles's law application, and we know that volume 1 is 12 liters.
So I'm just going to go right into Charles' law. 12 liters is volume 1.
Divided by 273 Kelvin, because this is your STP temperature.
So that's T1.
Equals X, because that's what we're solving for, X liters.
X liters, or V2.
V2, whatever you want to do. And then 523 Kelvin, because remember, you have to convert Celsius to Kelvin. Then
So that's the 250 Celsius change to.
And then you just do the math, and you find out it turns out to be 23 liters at 250 Celsius.
That's liters of water at 250 decimal point.
So for those of you who hate to label things, this is going to be pure misery. But now labels are more important than ever because you have to know at what condition, what the molecule is, and everything else, and what the unit is too. So there's 3 different things we have to know per question. All right, let's go on to B now.
Okay. So part B says what volume of oxygen at 20 degrees Celsius and 102.6 kilopascals is used if 640 liters of CO2 is produced, and the CO2 is also measured at the same temperature and pressure.
The key term there is same temperature and same pressure.
So then we know that the only thing that's varying is
the number of liters or moles.
Liters. Right.
So in this problem, this can be a lot faster since all variables are kept the same amongst pressure, temperature, and volume, and number of moles are going to change.
This is really just a straight gas stoichiometry. It's much like working at standard temperature and pressure, only we're not at standard temperature and pressure, but the conditions are changing. So
you can do a special thing here where you say 640 liters of CO2, and we can also read this equation that says 5 liters of oxygen reacts to form 3 liters of CO2. So this is a special step. It's not on our mole diagram. It requires a little bit of reasoning. But all you have to say is 5 liters of O2 on the top for every 3 liters of CO2. And you can only do this because the conditions are the same. I'm going to repeat that again. Because those conditions are the same, we can do this. If they were different, it would require us to use one of the gas laws. And this turns out simply to be 1,070 liters of O2.
With the sig figs.
Yep.
So, and again, we could have changed it to moles with the 22.4 like we did in the last one, but if you notice, that always ends up, you divide by the 22.4, then you multiply it back in at the end, and it kind of cancels itself out. So the big aha is like, yeah, these are moles, 1, 5, 3, and 4, but like Mr. Hunter just pointed out, as long as you're not changing the pressure and temperature conditions, those could just as easily be liters, because Avogadro's law tells us that moles kind of
at a constant temperature or the same volume.
The same. So that could be 1 liter at a given temperature pressure reacts with 5 liters to give 3 liters and 4 liters. Now it only works also for gaseous reactants and products, but that's a big time saver if you make that
you could do the other steps, but the liters would cancel out. So let's just go on to C and finish up this problem. So for C, it's asking if 465 milliliters of oxygen at STP is used in the reaction, what volume of CO2 measured at 37 degrees Celsius and 0.973 atmospheres is produced. So the first thing I would do is take note of what units they gave us. They gave us a temperature, a pressure, and STP. And good news, STP is both a temperature and a pressure. So we have sets of both. We have a volume that's in milliliters. We can keep it in milliliters, but just because the ideal gas law states we want it in liters, I'm going to convert it quickly to liters. It's just 0.465 liters of oxygen. So then we have to convert this to liters of O2. We're going to show you the whole math just to let you know, so using your mole island, 1 mole of O2 is 22.4 liters at STP. Since our initial conditions are at STP, we can use these numbers. Then 3 moles of CO2 divided by 5 moles of O2. And then lastly, it'd be 22.4 liters of O2 equals 1 mole of O2. So take note of what's going on with our numbers here. Notice the liters at both stages here, both here and here, are going to cancel out. So really, you could skip writing this step knowing that 1 liter or 3 liters of CO2 is equal to 5 liters.
Because the entire unit and
Number cancels. But so right here, you could just say, hey, that's 3 liters of CO2 and 5 liters of O2. But at the same token, we're just going to show you the full math just to help you visualize this. So when you hit enter, you get an answer of 279 liters of CO2 at STP. So then we have to decide which gas law we can use. This would be the combined gas law because they gave us a pressure, a volume, and a temperature.
There's our new temperature, there's our new pressure. We're
That gave us
supposed
a
to find
volume.
the new volume.
So it would be, we're just going to write it out for you. The combined gas law would be V2 equals 1 atmosphere, which would be your pressure 1, times 0.279 liters, which would be your volume 1.
That's what we just found.
Times 310 Kelvin, that's your temperature 2, divided by 273 Kelvin, which is your temperature 1, times 0.973, which is your pressure 2.
Atmospheres.
And if you hit enter on this, it turns out to be 0.325 liters. Notice he's canceling units with the liters remaining, so it's 0.325 liters of CO2 at the new condition.
New temperature and pressure that were specified up here.
Okay.
So we just did a simple gas stoichiometry problem here to get our volume, and then we used the combined gas law to get the volume at the different set of conditions.
All right. We'll assign you tomorrow the numbers you want you to do on the page 44 through 46, I believe. In the meantime, have a good day.